Hello, everyone. This is another live Q&A for MATH1055. I believe it's number 6. So halfway, this is the midpoint, I guess. So as usual, you can ask your questions using the chat, and we'll use the item pool to interact and solve a few problems together. So here is the link. As usual, you can go to this website, and let's suggest we start with this problem. So if you go to this webpage, itempool.com/maths1055/live, you will see this question asking you what is the sum of the following infinite series, and you see this sum 1/3 to the n, with n going from 1 to infinity. So this is just the reciprocals of the powers of 3 with integer positive integer exponents added up, all of them. So I hope you all you are all familiar with these types of series. This is an example of a geometric series because each term in the series is a fixed multiple of the previous one. In this case, it's 1/3. And we have in the lecture notes and the lecture videos, we have derived this geometric series formula, which allows you to calculate the sum of this infinite series when this quotient and the number q is between -1 and 1. This series converges, and it converges to 1/1 minus q. There is a slight difference between the series that you are asked to calculate and the geometric series formula. So please notice that the geometric series formula starts with 1, so q to the power 0. And in the series that we are calculating, we start with 1/3 to the first power. So the zero's term is missing. So you have to you have to compensate for that. Take your time to calculate the sum, and then we can all look at it together. I hope it's all clear. But do ask questions if something is unclear, or if you would like to make a comment, add some information. That's also good. That's also welcome. Okay, so I already see a good number of submissions. There are lots of individual ones. I don't know what those are, but we'll see. That's probably something like 40 to 50 people at the moment. So let's just wait a minute before I finish and reveal the answer. Again, all you have to do really is just apply this geometric series formula with now the quotient being 1/3, and starting with not n equals 0 but n equals 1, so you have to compensate for that term missing. Other than that, it should be relatively straightforward. By the way, I hope you liked the video, the intro video. So that's a demonstration of the harmonic series. If you looked at these stacks, you might have noticed that it's the overhang, the amount of which this stack of blocks had an overhang above the edge or over the edge of the table was the nth partial sum of the harmonic series halved. So actually, this bridge that I've built can be arbitrarily long. So as long as I want it, because the harmonic series diverges. If I had enough stacks, if I had enough blocks, I could have made arbitrarily long, like 2 miles long. But of course, I would have needed a lot of blocks because the harmonic series diverges very, very slowly, but it diverges to plus infinity. If you want to look up this problem with the blocks being stacked, you just have to Google block stacking problem or something along those lines. Okay, so I think there is a fair number of submissions and answers. Let me just reveal the answer here, and then we can move on. We can look at the problem. So let's see. So the answer was yes, 1/2. I might have forgotten to activate the system so it accepts equivalent answers. So whoever said 0.5, that's also correct. Just rest assured. Some people try to put it, yes, in a equivalent expression, but sort of using formulas. So that's my bad. So those 41 people got it right for sure. So let's just look at it together quickly. So all we had to do is apply the geometric series formula for so this formula with Q being 1/3. So this was the formula. And notice that we don't start at 0 in this problem of ours, but we start with we started with 1. Where do I point? So we started with n equals 1. So that's why we have to take this expression with Q equals 1/3. So I go from 0 to infinity with little n. But then let me just take this sum and subtract the first term, that is 1. Okay, so now I just use this formula. Again, this formula is only true if Q is between -1 and +1. So I use this formula, that's 1 divided by 1 minus 1/3. So that's 1 over 1 minus Q. Then I have to subtract 1. So what I have here in the denominator is 2/3. The reciprocal of 2/3 is 3/2. I have to subtract 1. So that's 1/2 minus 1 is just half. Okay, so this is how we got this number, this answer. Again, crucial point was that we started at 1, the first power. Okay. Actually, let me just show you a visual representation of this series. So let's see. So here is this image. So it says. So here you see a rectangle. Okay, my face is kind of covering up part of the picture, but you see this rectangle, and it's divided up into 3 parts, 3 equal parts. So that big, the largest rectangle, pink rectangle, is 1/3 of the total area. Then we take the middle third and divide that up into thirds. So that second largest pink rectangle is a third of the third of the area. So that's 1/9. And then we keep doing this, always dividing the middle third of what we have considered before into thirds, and considering one of these thirds. And you can see that this is just, if you want to add up these areas, you will get this infinite series, this geometric series. But if you look at the picture as a whole, you see this pink spiral and you see the white spiral, and they have the same area. So the pink spiral must make half of the area of the big rectangle. So that's just the visual representation. It's not an actual proof. It's just something that illustrates this fact. Okay, so let's move on, if that's all right. You can still ask your questions in the chat if you want. So here is an infinite series, and what I'm asking is whether it's convergent or not. So the infinite series that I want you to look at is 1 plus a fourth plus a seventh, and so on. So what I have here is multiples of 3 minus 2, but the reciprocals of multiples of 3 minus 2. Okay, so the key here, and I gave you this hint there below the question. There's that hint saying that try comparing the series to a simpler series, which you know to be convergent or divergent. So if you just look at this series and don't look at the details, but sort of the general behavior of the series, of the general term, we have 1/3 and minus 1. So that looks a bit like 1/n. So that's the general feeling that we get if you look at this general term. So you would expect it to behave similarly to the harmonic series, which is just the sum of reciprocals of positive integers. So try comparing it to the harmonic series or some multiple of the harmonic series, because if you can compare it to a series like that, you might be able to say, okay, because the harmonic series is divergent, this series must diverge as well. But of course, it might be not possible. So that's the actual challenge here, to make this comparison series and use what we know already from the lectures. Okay, so the two possibilities, of course, are yes, it is convergent, or no, it's divergent. Okay, so I hope, so if you haven't seen the harmonic series before watching the lecture videos or looking at the lecture notes, I hope you were really shocked by the fact that it's divergent. I mean, it is, as with everything involving infinities and infinitely many things, there are surprising results. So when you look at a geometric series like the one in the previous question, you are adding up infinitely many numbers. They are getting smaller and smaller. In fact, the general term tends to 0. But even though you are adding up infinitely many numbers, they are getting small in such a way that the sum of these infinitely many numbers is a finite number. While in the harmonic series, you are adding up infinitely many numbers. They are getting smaller and smaller. In fact, the general term goes to 0, yet it is divergent. And if you remember from the lectures, what we did there, we were actually comparing it to the partial sums to a smaller thing that definitely is divergent and diverges to plus infinity. Okay, So I see it's kind of funny to see that we have almost the same number of votes for the two possibilities, and actually one just overtook the other one. I don't know if you noticed. Yes, well, I don't want to talk about politics in these sessions, but so yeah, it's really interesting to see that. So it's okay if you don't get it right. Yes, let's just be careful here. So if it's okay if you don't get it right this time. We are here to learn, and hopefully through these questions you will all be able to understand what's going on with these convergent and divergent series. Okay, so there are 90 people who have voted, which is good. There's 116 of you. So let's probably, yeah, we can just finish this poll and reveal the answer. So yes, it is. Well, the answer is no. It is divergent. So the people who have voted for divergence is right, but there is a good number of people, well, an almost equal number of people who have voted for convergence. So let's just take some time here and look at it together. So we have this series consisting of terms which in general look like this. So 1 divided by 3 and minus 2, right? So if, well, the first thing you want to do if you are presented with an infinite series like this is you want to look at the general term and you want to get an idea. You should get an idea as how it behaves, about how it behaves. So this is, as I said, this is 1 divided by a linear expression in n. So it's kind of decreasing, going to 0, but going to 0 linearly. So just like the harmonic series, the terms in the harmonic series. So what we would like to do, so that's already a hint. If you have to have an initial guess, and our guess is that this is something like 1 over 3 to the n, and for large n. I hope you all agree that if n is really large, like a million or a billion, multiplying it by 3, so 3 million or 3 billion, will not even feel if you just subtract, 2 of it and take the reciprocal. So these two numbers are really close for large n. So, and that is the key to notice this, because if you notice this, then you can get a first idea as to whether it's convergent or divergent, the infinite series. So because of this reason, because of this sort of estimation, this approximation, you could say that it is behaving like a harmonic series or like a multiple of the harmonic series, because of course 1 over 3n can be written as 1/3 times 1 over n. So it's behaving like the third of the harmonic series, but that still should be divergent. So if you have this first idea, so that it should be divergent, at this point, let me put a question mark there, because we haven't proved anything. We just sort of got a general idea. And now we can go on to coming up with a comparison series. So what do we want to do in this case? Well, if you want to really prove that this series is divergent and you want to compare it to the harmonic series, prove that it is just like the harmonic series, it's divergent, you should be able to compare it to the harmonic series in a way that you write a series that looks like the harmonic series but is smaller. Okay, so you should write something that is smaller but still divergent, because if you put here something that is smaller but goes to infinity, because of this inequality, it will push the other series with itself up to infinity, right? All the way to infinity. So the way I would write this is, we have the nth partial sum of this original series, so 1/3n minus 2, with little n going from 1 to capital N. Okay, so this is the capital Nth partial sum of the series. We are just adding up the first capital N terms, and each of these terms can be given the lower bound. Now let's think about this. If we write 1/3n for each term, we get something that is smaller. So why is that? Yeah, just think about the denominators. So 3n is greater than 3n minus 2. So if we divide 1 by a number that is greater, we get a smaller number. So for each of the terms, we get something that's smaller. So if we add those up, we get something that's definitely smaller. So that's just, as I said, that's 1/3 times the capital Nth partial sum of the harmonic series. Okay, and this is basically the proof, because then if we take capital N to infinity, so we take the limit of the partial sums. Let me denote this by Sn, and the other one by little sn, capital N. As capital N goes to infinity, this thing, which is the smaller, less than the other side, goes to infinity. So the other side, the greater thing must also diverge to infinity. Okay, so that's the general idea. Okay, so let me just go back then again and try to say it again, but a bit slower maybe. You got the answer? Okay, so the idea is that 3n multiples of 3 are greater than multiples of 3 minus 2, right? So this number is greater than this number. So if I divide 1 by a number that is greater than the other, I will get something that is less than the reciprocal of this other thing. Okay, for all, I should say, for all n that are these positive integers. Okay, is that clear? So that's the idea, and then you are just comparing the partial sums, but each of these terms on the right hand side is smaller than on the left hand side. So the whole partial sum, okay, cool, is less than the other one, which and the smaller thing diverges, so the other one must diverge as well. Okay, so let's go back to the problems then. Feel free to ask questions if you have any. Here is another infinite series. It's the sum of n minus 1 divided by n cubed plus 1 with little n going from 2 to infinity. So the numbers that you get here are 1/9, then 2/28, then 3/65. So you always have a cube, number cubed plus 1 in the denominator, and you have the natural numbers in the numerator. Okay, and again, you should decide whether it's convergent or divergent. And again, the hint is the same as in the previous question. Try comparing it to a series that is simpler than this one, but you know something, you know about its convergence. And again, what I would recommend you to do is look at the general term. So you look at the general term n minus 1 divided by n cubed plus 1, and think of its values, and n is really large, is a big number, and try to compare it to another series about which we know if it's convergent or divergent, and compare it to that other series in a way that actually helps you answer the question. Okay, so I'll give you a minute or two, then we'll and I'll reveal the answer and also show you how to correctly use the comparison theorem, well, the limit comparison or comparison sequence in this case, comparison series, I should say. So there was a question, I believe, in the chat which I haven't answered yet. So why do we need to compare it below, from below? Why couldn't I just finish the proof after I get this 1/3 over 1/3 times 1 over n in the previous question? But the point is that this trick that I'm just writing 1 over 3n instead of 1 over 3n minus 2 and getting a smaller thing, it worked in this case. But what if I had something like the sum of 1 over 3n plus 2, not minus 2? How would you estimate that series, or the terms in that series? So then I couldn't write 1 over 3n, because then that would be a greater number. I'll talk about this in a bit more detail when I switch to the notepad. Okay, so there are 80 answers. So that's actually a very good question. I'll talk about that in a second. So okay, we have a good number of answers. Let me just wait another minute in case some people are still sort of trying to convince themselves about this comparison. So again, we'll look at this general term and try to get a feel for its sort of decay rate, and see if we can compare it to a series that we have seen before in the lectures. Okay, I don't see too many new answers appearing, so let me just finish the question and reveal the answer. So yes, it is convergent, and in this case there were more, the ratio of correct answers to incorrect answers was greater, which is good. So let me first quickly go back to this previous problem. So what if we had plus 2 in the denominator, not minus 2? Then this reasoning couldn't have worked, right? because 3n plus 2 is greater than 3n, so it would be the opposite inequalities. So I couldn't just do this. But then what we could have done is, of course, 3n is 1 over 3n is greater than 1 over 3n minus 3n plus 2, but 1 over 4n, let's say, should be smaller, starting at some index, starting at some number than 1 over 3n plus 2. So let me just quickly show you what I mean. So if I had 1 over 3n plus 2 for the general term, I couldn't have used, well, drop that plus 2, because then I would get something that's actually bigger, okay, because I'm dividing by a smaller number. So I should divide by a bigger number, something like 4n, but still linear in n, okay? So if you think about this, so what about this inequality? Well, let me just rearrange this. 4n is greater than 3n plus 2. I just cross multiplied. Let's take away 3n from both sides. So this is actually true for all n that are greater than 2. Okay, so I can kind of compare the sum of these numbers to the sum of these numbers for all numbers that are greater than 2. So starting from the third term, for n equals 3, I already have this inequality. And the first few terms are sort of finite, so they don't make a real difference in the behavior of convergence or divergence of the sequence or the series. Okay. I hope this makes sense, that if we have plus 2, then we have to be slightly more clever in our use of estimates. Okay, so I hope that was clear. And oh, by the way, I should go back and just sorry, let me finish and review. So in the previous one, well, the last question, what happened? Let's there was. So what happened there is we had the general term being n minus 1 divided by n cubed plus 1. So for large n, again, adding 1 to n or subtracting 1 from n or adding 1 to n cubed makes kind of no difference if n is really big. So this behaves kind of like n over n cubed or 1 over n squared. Okay, just if now is the time that you can use your calculator and plug in n equals million into these two sides, and you will get similar results, similar answers. Okay, for large n. Okay, so this is not a proof of anything. This is just you trying to get an idea for the behavior of the sequence or the series that you are looking at. So now what we should do is we should look at so from this fact, we should sort of conclude, or not conclude, but guess that it should be convergent. Again, let me just put a question mark there. So we are guessing that it's a convergent series, the sum of these numbers from n going from 2 to infinity. We're guessing that it should be convergent because the sum of reciprocals of square number is convergent, and that is something that you can read in the lecture notes. So we know that the sum of these numbers converges. The sum of these numbers is finite. So how should we compare this? Well, let's look at the capital nth partial sum this infinite series, and we can actually do the same trick, but now that we did in the previous problem, but now in the opposite direction, because now we want to show that this sum, but this is definitely non-negative. We are adding up positive numbers, so 0 is definitely a lower bound for the whole sum. We are not getting anything negative. But what we could do with this fraction, well, we get something that is bigger if we write n instead of n minus 1, right? So that should be giving us something that is bigger if we write a bigger numerator, and if we write a smaller denominator, we should get something that's even bigger, even larger than that. Okay, so just by looking at this general term and coming up with a upper estimate by increasing the numerator and decreasing the denominator, we actually have found that the nth partial sum of the series that we are interested in can be dominated or given the upper bound of the nth partial sum of a series that we know to be convergent. So if n goes to infinity, and this is finite. This is a finite number as n goes to capital N goes to infinity. Okay, the sequence of partial sums, more and more terms we add up, we still get a finite number, even if it's infinitely many terms, even if we take the limit of this sequence. So this is finite, and of course this means that we are between 0 and some finite number in the limit. Okay, so this is why we have convergence of this sequence of partial sums, because we have something that is greater than this partial sum, and that thing goes to a finite number. Okay, there is an actual this can be exactly found to be, this is just as a curiosity, can be found to be pi squared over 6 minus 1, but you don't have to believe me or don't have to worry about this. But it's a really nice sum, this one. Okay, I hope that was again acceptable and clear. Do let me know if it wasn't entirely clear. That's the general idea. You always want to get an initial feel for the series that you are looking at, and you can do that by looking at the general term and try to compare it to something that you already know about. All right, so the next question, let me just put it link in the chat again. So itempool.com/math1055/live. So question 3, the previous question, okay, so that was convergent again, because we had positive numbers added up, and we had something that was greater, that has partial sums that are greater than every partial sum of the series that we are interested in, and those greater partial sums converge to a finite number. So the smaller partial sums cannot go beyond that number. Okay, it's like a ceiling for the sequence of partial sums. I hope that's clear, but please do let me know if this still doesn't make sense. Then I can go back to the example and show you again. It's very important that we get this right, and it's clear for everyone, because these are the more important parts of these topics of this topic of infinite series. Okay, so the next problem in the meantime is on. I started accepting answers. So express the following repeating decimal as a fraction of two integers in lowest terms, and we have the number 0.123, infinitely repeating. So now, again, it's time to realize that here we have something that's infinitely repeating. So, and what we have is we have 0.123 what is it, thousands. So 123 divided by 1,000 will give you the first three digits, and that has to be repeated. So if you want to get the next three digits, you have to take 123 divided by 1,000,000, right? So that way you get the next three digits, which is 1,000 squared, 1,000,000. So you might notice something there. Okay, so there is a question in the chat. So the simplified convergent part is greater than the yes. No, you are actually answering it, right? You can still prove. Yes, yes. So it could happen. Of course, that example that we had, there we could use 1 over n squared as an upper bound. Again, we could have something that we had in the first question, where we can't just drop terms in the original fraction and come up with a simple upper bound like 1 over n squared. But you can always make it correct, add terms, so that you actually get an upper bound which is a multiple of 1 over n squared. Okay. I'll show you what I mean in a minute. But in the meantime, let's just concentrate on this question. Okay, there is already 60 something. Submissions. Okay, let me just reveal this because it's not the most important question, but this is a kind of problem that you can actually solve using, now I can say, the geometric series. Again, I forgot to accept equivalent answers, so people who have written 123 divided by 999 were also correct, but if you look at the problem, the question, it says in lowest terms, so you might have not noticed that you can simplify by 3 to get 41 over 333. Okay, so we'll look at this problem in a second, but let me just quickly go back to the previous one. So if we had n plus 1 divided by n cubed, what we had, let me just, plus 1. So instead of minus 1 here, we had plus 1. We could have given the upper bound of n plus n. Okay, so not dropping this term, because if we just drop the plus 1, we get something that is smaller, but adding n instead, which definitely which will definitely give us a greater number. But then we have here 2n divided by n cubed plus 1, right? Okay, and then we could have again just drop that plus 1 to get 2 times 1 over n squared. Okay, so this is what I meant. If 1 over n squared is not an upper bound, a multiple of 1 over n squared will actually give you a good upper bound. So that was the point. Okay, I hope that's clear. So let's go back to Well, let's move on to this other question where we had 0.123, infinitely repeating. So the point here is to notice that you have 123 times 1 over 1,000 plus 1 over 1,000 squared plus 1 over 1,000 cubed, and so on. Okay, so this number is equal to 123 times this geometric series. Let me write it in a way that you might recognize it. Okay, with n going from 1 to infinity. So this is the geometric series that we wanted to look at. And again, applying the geometric series formula means that it's 1 divided by 1 minus the quotient, that's 1/1000. Of course, that would be the answer if we started at the zeros power. So we have to subtract the first term from the geometric series from the full geometric series to get the correct answer. And for this is just, of course, 999 over 1,000. We take the reciprocal and then we subtract 1 to get 1 over 999 times 123. And so this fraction can be simplified by 3 to get 41. So 41 times 3 is 123, and 333 times 3 would be 999. Okay, so that was the idea there. Okay, let me go to the next question. And so here we have another infinite series. It's the sum of 2k squared divided by k squared plus k, with k going from 1 to infinity. The question it's whether it's a convergence series, and my hint is to you is to apply the vanishing test now. So remember, the vanishing test is a test which you use to check whether the series can converge at all. Okay, so just look at the general terms in that series, and you will notice that these numbers that you are adding up in the limit when k is really big, they are not getting smaller and smaller. Okay, so that's a hint. That's a big hint. Okay, I'll only take a minute on this question because we are short on time, and we still have some few questions that I would like to get to, if that's okay. You can of course leave the session if you have someplace else to be. Feel free to leave the session. I will only take a few more minutes of your time, and then I'll let you go. Okay, so there's already a good number of submissions. Let me just close the poll right here because this is not the most interesting of questions, although it is important. So let me just close it. Sorry if anyone wanted to vote and couldn't. So the idea that it's divergent for sure because it fails the vanishing test. Remember, the vanishing test says that the general terms in the sequence should go to 0. And here we have terms like this: 2k squared divided by k squared plus k. And that, in fact, goes to 2 as k goes to infinity. Okay, so the problem is that the terms in the sequence don't get small. So we are adding up numbers that are getting closer and closer to the number 2. So you definitely will get a divergent sequence. Okay, so remember, remember the vanishing test only tells you if a sequence can converge. If it fails the vanishing test like this one, that means that it's divergent. But if it passes the vanishing test, then it means that it can be convergent, but not necessarily convergent if the general term goes to 0. All right. So this is the last question I want us to consider, and then I'll let you go. So here we have an infinite series. The sum of 3 to the power k divided by 4 to the power k times k cubed, with k going from 1 to infinity. Is it convergent? And my hint, so what I'm telling you to use, is the ratio test. So you might remember from the lectures that the ratio test is taking the limit of the ratio of the consecutive terms. So taking the n plus first term divided by the nth term and letting n go to infinity. If you look at this ratio, well, in absolute values, if you look at this ratio, it might tell you if it's convergent or divergent. If the ratio of consecutive terms is less than 1, positive, it is a convergent sequence, and if the ratio converges to a number that's bigger than 1, it's a divergent sequence. The ratio test, I believe, was discussed in the lecture. In the lectures. So let me have a look. Oh, okay. You're correct. There was no video on the ratio test yet. Oh, that's my bad. Sorry. You are completely right. Yeah, the videos we are not there yet with the videos, but the lecture notes had the ratio test in it. Okay, it's okay if you don't know how to apply it yet. Sorry for this this confusion. That's my bad. You'll see the ratio test in next week's videos. So on Monday you will by the end of Monday you should be you should know what the ratio test is. Sorry, let me just finish the poll then. I hope some people got it right anyway. Yes, so it is convergent. We'll look at it next week, if that's okay. Basically, if you apply this ratio test, you will see that the ratio of consecutive terms in the sequence tend to a number that is less than 1, which proves by this theorem, the ratio test, that it is a convergent series. But we'll look at it next week. So thank you for everyone who attended this live lecture, and have a nice weekend, people. Take care of yourselves. I'll see you next Friday with the ratio test.